I found a product that has defects, so my goal is to analyze it. Hey guys, welcome back to my YouTube channel. So in this video, I'll be sharing with you my data analysis project. My project is related to statistical quality control. So let's get into it. Alright guys, so here's the project that I worked on. My project is analyzing and reducing the impact of defects on product quality and repair costs. And this is a company called Precision Tech Manufacturing that I used. So let me give you a storytelling. Imagine walking through a bustling manufacturing plant where every machine hums in perfect harmony, each producing the intricate components that make up a larger product. But amidst the rhythmic clatter and whirring of machinery, there lurks an invisible threat defects. These defects are more than just minor flaws. They are the silent culprits that can erode the efficiency of the production line, escalate costs, and ultimately tarnish the reputation of the final product. As a data analyst tasked with uncovering the hidden patterns in this manufacturing process, my mission was to delve deep into the data and reveal the impact of these defects on the overall repair costs. But this was not just about numbers, it was about understanding the story behind those numbers, and they could drive actionable insights to improve the manufacturing process. So also in my project, I utilized Power BI for its robust data visualization capacities, allowing me to create clear and insightful charts like the X bars and the donut charts that reveal patterns in repair costs associated with different defect types and manufacturing process. And the software's interactive and user-friendly interface made it easy to explore the data, identify insights, and communicate these findings effectively to the manufacturing teams, drive informs. So here's the data set and the software I used. I got it from Kaggle, and you can see it has 8 columns with a lot of rows. So this is what it is. So here's the overall results. My question is, how does the mean of repair costs for manufacturing defect vary over time, and are there any significant deviations from the process means that could indicate issues? So this is a statistical quality control using an X bar on the right side, and on the left side I calculate the mean, which is 5.05363, and the standard deviation, which is 146.2552. And we can interpretate the mean repair cost of $505.34, that this cost provides an estimate of the average cost incurred for repairs per defect date, and this value serves as a central tendency metric, giving a sense of what the typical repair cost might be on any given day. And also the standard deviation of the $146.26 indicates the level of variability in the repair costs across different defective rate dates. And a higher standard deviation suggests more significant fluctuations in repair costs, while a lower standard deviation would indicate that the repair costs are more consistent day to day. And given the relatively large standard deviation compared to the mean, it suggests that the repair costs vary quite a bit across different days. And this variability might be due to the nature of defects, the severity of the defects, or other factors influencing the repair costs on specific days. And we can also see that the X bar is plotting the mean repair costs for manufacturing over time. And we can see that the green line here represents the overall process means, while the red dashed lines indicate the control limits. So up here would be the upper and the lower control limits, which is set at plus or minus 3 standard deviations from the mean. And the standard deviations from the means is the repair costs vary significantly over time, with several points exceeding the upper control limit, indicating that there may be special causes of variations that may need to be investigated. And the process behavior is basically the process is not entirely stable, as there are no points above and below the control limits, suggesting that uncertain periods experience unusually high or low repair costs, and these could correspond to specific incidents or issues in the manufacturing process. But you can see up here, it falls within the limit, it falls below it. See down here probably in late June, that's when it exceeds the lower limit. So there has to be some kind of investigation going on. And here I use Python, and this is what is the impact of different defect types on the overall repair cost in our manufacturing process. So you can see that there, based on the output, we see that there are three defect types: cosmetic, functional, and structural, and its total repair cost and its average repair cost. And let me go through each one. So the structural defects is for cosmetic is 178,797, and these defects have the lowest total repair costs. While still costly, typically don't affect the functionality or safety of the product, leading to lower repair costs compared to structural or functional defects. And then the next one is functional, which is the second highest, which is 171,905,058, and it might impact the operations or usability of the product, leading to significant repair expenses. And finally, the highest is structural, which is $176,923.85. And this suggests that structural defects are the most expensive to fix overall, possibly due to the complexity or critical nature of these defects in the manufacturing process. And we see that the average repair cost for cosmetic defects is $513.91 per defect, and despite having the lowest total repair cost, this could indicate that each cosmetic defect requires a relatively high cost to correct, perhaps due to the precision needed in repairs to maintain product aesthetics. And then next we have the functional defects, which has the average repair cost is $507.10, and these defects are slightly cheaper to fix on average, but compared to cosmetic defects, but still represent a significant cost, reflecting the importance of ensuring product functionality. And finally, we can see that structural defects have the highest total repair cost. The average repair cost is the lowest at $502.62, and this may indicate that while structural defects occur frequently, each defect is less costly to fix compared to other types. You can see here's a bar chart that displays the total repair costs associated with different defect types. And you can see that all defect types contribute significantly to the overall repair cost, with cosmetics and functional defects having a similar total repair cost. And structural defects have a slightly lower total cost compared to the other two. And this chart allows me to quickly identify which defect types are the most and least costly in the manufacturing process. Although the differences are not vast, cosmetic and functional defects appear to be the areas of focus for cost reduction efforts. And here's the donut chart I use in Power BI. And the question I asked is, what is the portion of the total repair cost attributed to each defect type? And which defect type is the most costly in our manufacturing process? So overall, you could see, like I said, there's the defect type, the structural, functional, and cosmetic. And the donut chart provides here a visualization of how the total repair costs are distributed across different defect types. And we can see that structural defects take up the largest portion, which means that they are the most expensive in the manufacturing process, and address these could yield to significant cost savings. So understanding the proportions helps prioritize efforts to reduce costs. For instance, if cosmetic defects are disproportionately costly, it might focus on improving quality control measures related to cosmetic issues to reduce their occurrence and associated costs. So let me give a summary and conclusion. So we can see that the expert provided a time series view of mean repair costs over time. It highlighted periods where repair costs deviated significantly from the process mean, potentially indicating issues in the manufacturing process that need further investigation. And the patterns observed in the X bar chart suggest that there may be cyclical or seasonal trends in repair costs. As more data is collected, predictive models could be developed to anticipate when defects are likely to occur, enabling proactive maintenance and reducing unexpected repair costs. We also see that the bar chart analysis showed the total and average repair costs attributed to different defect types. And the results revealed that certain defect types, such as functional and structurals, may have a more significant financial impact on the manufacturing process compared to others. And the donut chart effectively illustrated the proportion of the total repair costs attributed to each defect type. And as manufacturing technology continues to evolve, incorporating advanced analytical tools such as machine learning or AI-driven quality control systems could further reduce defect rates and associated repair costs. And future interpretations should consider the potential impact of these technologies on improving manufacturing efficiencies and product qualities. And also, I want to bring up the sustainability and cost efficiency. Is that the analysis could be extended to assess the environmental impacts of defects and repairs. For example, defects that require significant material waste or energy-intensive repairs could be targeted for reductions not only to lower costs but also to enhance sustainability. This could become more increasingly important as regulatory pressures and consumers' expectations around sustainability grow. And beyond the financial implications, future interpretations should also consider how defect types and repair costs impact customer satisfaction and brand reputations. And defects that lead to higher repair costs may also correlate with product failures that affect customer perceptions. And focusing on reducing these defects could improve customer satisfaction, leading to higher brand loyalty and repeat businesses. So thanks for watching, and please subscribe to my channel.